This is going to be a series about computational redstone, and we're going to start off with binary. We need binary for computers to function. We could technically also use hexadecimal with comparators, but that's a lot more difficult. I may do videos about them though, because it is quite a lot of fun. So let's start off with the basics. How do we read binary values? What does this even mean? Well, here I'm doing an add operation, and before we can even understand what is happening here, we need to look at the values. So, what is 101? And by the way, everything to the left of this is just zeros. This goes on forever and ever, just like in decimal. Decimal is just every value from 0 to 9, and if you want to go higher than that, then you will need to use another digit. So if you want to show 10, for example, then we actually need 2 digits. This is 19, but you get the point. Now in binary, you only have a 0 and a 1. So how will we show a 2? Well, just like a 10, we just go to the next digit. Now the binary numbers will only be 3 high, because then you can see the difference between a decimal and binary. So this is not a 10, it's actually a 2 in binary. We have to go to the next digit because we couldn't fit a 2 in this one right here. So how will we do a 3? Well, that's simple enough. It's just a 1 and a 1. It's a little difficult to read though. Let's explain the math behind why this works. And this right here is actually 2 to the power of 0, which is just a 1. Why is it important? Well, if you want to convert a binary value into decimal, you just want to add up all the ones with their correct position, and that way you get the value. So this digit right here will be 2 to the power of 1. This will be 2 to the power of 2, which this is just 4. This is just a 2, and this is a 1. So every time we go 1 to the left, it doubles the value. So the next one is going to be 8, the one after that is going to be 16. It's just multiply by 2, multiply by 2. If there was a 1 here, it would actually correspond to an 8. While if this was a decimal number, it would actually be 1000. So we're giving values depending on how much digits it went to the left. If we have a 0 here, we don't add this to our decimal number. So now let's start to convert this with an extra 1 over here. We've already added the sign, so it's pretty easy. We just do 8 plus 4 and then plus 1, because this one is a 0. And 8 plus 4 plus 1 is 13. So yeah, we just successfully converted a binary number into decimal. Now here we have a 5 because it's 4 plus 1. And this one is 2 plus 1, which is 3. Now what is 5 plus 3? Well, it's 8. Let me just fix this value right here. If you're wondering what this top number right here is, it's going to be the carry line for the addition. So how do we calculate this? In order to calculate addition, you need to know about logic gates, and I have them right over here. So let's start with a NOT gate, which just inverts the input and gives an output. So this is the input, it's the lever, and the output is the lamp. So the lever is currently off, however the output is on. If I turn on the lever, it's the exact opposite. Then we have the OR gate, which checks if this one is on or this one is on, and then the output goes on. In Minecraft we can do that really easily by just connecting them up, and there you go. If one of these is on, the output is on. Then we have the AND gate, which only turns on if both this one is on and the other one is on. We can do that with 3 NOT gates. We NOT both outputs, but why? Well, both these storages need to be off for this redstone to turn off. So if one is off, it's not enough. We need 2 of them to be off. There we go. And when this is off, storage turns on and then turns on the lamp. And that's how an AND gate works. Now we also have a NOR gate, which is just a NOT OR gate. To make that, you just have to add a NOT to the back of it. And the same goes for a NAND gate. In order to make a NAND gate, you can either add an extra torch, like so, or some other way. Or the more easy approach for a NAND gate is just to get rid of that torch, because it's just double inversion. It's not required. But I'm gonna keep it like that. Now let's talk about XOR gates, or exclusive OR gates. An XOR gate only outputs a 1 if only one of the inputs is on. If both are on, it will output a 0. The 1 goes into this OR gate right here, and then goes into some AND gate to turn it on. This AND gate actually already has both values turned on. So what is that other value? Well, this other value comes from the NAND gate, which is just, well, an AND gate but inverted, and that AND gate comes from the inputs. But why? See it like this. If both of these levers are on, then this redstone will turn off, and we don't want an input if both of them are on, so we just put this into another AND gate. And because this is now off, the AND gate right here will output a 0, because both of them need to be on. There are simpler designs. That one is just to show the concept of an XOR gate, but here we have roughly the same idea, but it's much smaller. This is our AND gate. It's actually a NAND gate. It just turns on both of these OR gates, and this is just a double inversion, or 2 NOT gates. So this turns off, and whenever the AND gate is on, it will turn it on again, which will stop the output from flowing. And here is the double inversion again. It's just 2 NOT gates. Then here we have an XOR gate with comparators, and as you can see, it works. If one of them is on, it's on. Both are on, it's off. And it works by turning on the opposite comparator. So currently it's subtracting from its own comparator at the left, which is like subtracting 15 from 15, and 15 minus 15 is 0. However, here it goes to this comparator, and because it can't turn on this redstone, it goes true. Now there's another version of this which has 2 pieces of redstone dust, and you would think it wouldn't work now, but it does, because if I turn this on, this one is 13 signal strength. However, this one is 11, and 13 minus 11 is still 2, so it's still going to be on nonetheless. And if you don't know what comparator subtraction mode is yet, then you should do some research. Oh boy, you're gonna need this. We're gonna use this a lot. But yeah, those are logic gates. But how do we use these in addition? Well, in order to do addition, you just need to do an XOR. 1 XOR 1, which you can just simulate over here, is going to be a 0. We know that the sum of A and B at least is going to be 0. However, what if we are going to be carrying digits? Because 1 and 1, 1 plus 1 is 2. We need to carry a 1 to the next digit. How do we do that? Well, we just add it to the carry line, and then we XOR this carry with the sum of A and B, which is just another XOR. So we're XORing an XOR, if that makes sense. First, we XOR 0 and 1, which let's simulate that. That's a 1. This right here is going to result in a 1. However, this is a 0. And the reason for that is because we have to XOR 1 that we got from this with that 1. And 1 XOR 1 is 0. If we AND these two, 1 and 1, then you know that the output is going to be on. And that's how we check for a carry. So we just need to check, is A 1 and is B 1? Then we want to carry a bit to the next digit. And also, if the carry is a 1 and the sum of these two values is also a 1, then we want to carry as well. So we call this bit right here, the most to the right, the carry in, and the one that is the most to the left, the carry out. And the carry out is not actually this one, it's this one, which is out of bounds. We call this the overflow bit because our addition is a maximum of 4 bits right here. I ignored the zeros at these positions, however they are actually there. So yeah, that's an overflow bit, or the carry out, whatever you want to call it. And that bit is the carry in. And because that is a 1 now, 1 XOR 0 is a 1. So that will result in a 1. However, it will still carry over because A and B. If we AND A and B, it's going to be a 1. However, because XORing this is going to be 0 now, 0 XOR 1 is going to be equal to a 1. And our result is 9. So 5 plus 3 plus that carry in, which is a 1, will result in 9, which is just 8 plus 1. That was pretty complicated. The actual circuitry is not as complicated. We have a XOR, which I guess you can also call a half adder. And here we have the carry in line, which goes into the next XOR. And these AND gates of the XOR both go into this carry out line, which just goes into the next carry in of the next digit. So if it's a 1, the output's a 1. If both are on, then the carry line turns on and goes into this XOR and powers this lamp. If we then put in a 1 here, it will go to the next one. Now we're actually doing 3 plus 1, which is 4. And we could actually make this 5 by turning on the carry in. But there are many more ways to get 5. This is our overflow bit because I only have 2 modules. However, you normally have 8 or 16 or 32 modules because else you can't really get very big numbers. For example, currently I can only really add a 3 and a 1 and I'm already at the overflow bit. The max I can represent with just 2 bits is 3, which isn't a lot. I want to be able to do big additions. For example, 5 plus 8 or even 116 plus 512. All of that stuff is only possible by adding more modules. And our CPU is either going to be having 8 or 16 bits. Subtraction is a little more complicated. Let me show you why. So let's do 5 minus 3. Actually, let's not subtract, but instead just add with the negative 3. So I actually need to explain a little for you to understand. Let's say I have some number, a 5. Doing 5 minus 3 is actually the same as adding negative 3 to 5. 5 plus negative 3 is just 5 minus 3. We just get rid of this addition sign and we get the same thing. Now in both cases, they're equal to 2. And we can do the same with binary. But how do you get this negative number? How do we make negative numbers? Well, it's actually pretty simple. For this we have 2 methods. One is called 1's complement and the other is called 2's complement. However, it depends on what you're creating. Usually you will need 2's complement if you want normal binary numbers though. Okay, in order to do 2's complement, we invert this tree. Well, it's pretty simple. We just put all of these values into a NOT gate or some kind of other method to invert them, which I will show later on. It's pretty clever. But this isn't the 2's complement. What we just did is 1's complement, and that's just inverting all of the bits of this of the second number. Let's just see what happens by just addition. So this is pretty easy. 1 XOR 0 is 1, 0 XOR 0 is 0, 1 XOR 1 is a 0 with a carry. So we go to this one, and 1 XOR 1 is again a 0. So it's going to be an overflow. And for subtraction, we use that overflow bit to check if the number is positive. And if it's a 1, it's positive, it's a 0, it's negative. Now 5 minus 3 is 2. However, our subtraction gave a positive 1. And that's where 2's complement becomes handy, because if we add a 1 in the carry-in, then this 1 will turn into a 2. And why is because 1 plus 1 is going to be 2, so it's going to need to carry, and then this digit becomes 1. So what we just did to convert from 1's complement to 2's complement is literally set the carry-in bit to a 1. That's all. That's 2's complement. We just invert B and then add a 1 by turning on the carry-in. And we can simulate this right here as well. Let's say I want to do 3 and then minus a 1. To do that, we need to invert a 1. And instead of then turning on this lever, we have to turn on this lever, the 2's place. And we turn on the carry-in. And there we go. It's a positive and it's 2. So 3 minus 1 is a positive 2. Pretty clever. So that's how you do subtraction. And that's about enough information for addition and subtraction. We also have multiplication and division, which primarily use addition and subtraction. However, they use one extra thing, actually 2 extra things, and those are called rotates and shifts. And let's say I have a value of 5. And we have this big line right here, and this is the depth barrier. Every number that gets passed here will die out. And this depth barrier is only there for shifts. This doesn't exist for rotates. In fact, it's actually a teleporter for rotates. We'll get into that soon. So if we shift 5 to the right, then we just move all of the digits 1 over. So this 1 right here will become a 0, and this one will become a 1, this will become a 0. However, the 1 to the right moved to the right side of the barrier. Now this depth barrier doesn't like any numbers, so it just completely gets rid of that 1. And now we only have 0 and 0 left. So the 5 got chopped into a 2, which is the same as just dividing the number by 2 and then getting the floor of it, which is just rounding it down in basic terms. Our 5 first got divided by 2, which is just a shift to the right, which is actually 2.5. But because our depth barrier got rid of the value instead of just keeping it, the 0.5 got lost. So we just round it down. And this is nice in most circumstances. However, with division, it will be a little different because we also want to keep the decimal precision. So yeah, we just round down the number. But what happens if we shift to the left? Well, it's the exact opposite. Instead of dividing by 2, we multiply by 2. So 5 will become 10, because that's just it multiplied by 2. And to prove that, all you have to do is go back to a 5. And we'll actually need one more digit right here. And then this one will go to the left, so it will become a 1. This one will become a 0, and this one will become a 1. And now it's a 10, because 8 plus 2 is 10 instead of just 5. Now rotating has teleporters. So rotating is the same as shifting. However, all of the numbers that go past a barrier will just teleport to the other side of the number. So if we rotate to the left, which is the same as multiplying by 2, then this 1 will become a 0, gets cut off, and the 1 will actually go here because of the teleporter, and then this 1 just shifts normally. So it's just a shift, but the digit the most to the left will go to the back of the number. So our 10 became a 5 again. So it kind of did a right shift. So this isn't actually a right shift. We're back at 5. Let's rotate to the right again. So I just made that a 0 again. Now the 1 is over here, so we'll just move the spot to the right. This one will become a 0 again. And the 1 will step through the portal, and it will be here again. So it's now a 10. Now, rotating doesn't necessarily double or halve the number. It's pretty random. So right here, I have an 8 and a 3, which in total is 11. Okay, I'm going to move this barrier teleporter, just so it's not in our way. When we rotate this to the left, it goes from 11 to a 7, because these two shift and the 1 step through the teleporter, so this digit becomes 1. So I went from 11 to 7. That's rotating and shifting. And at the moment, I've only really explained theories, and I haven't really made any circuitry yet. We will do more of this in the next episode, but that about wraps it up for today. Thank you guys for watching, and I hope you understood. If you have any questions, just put them in the comments. Make sure to subscribe, and yeah, like the video, please. By the way, this is my console world. It's made on Wii U, and I tried to replicate it block by block with my hands, except it's really tedious. Don't do this yourself. I kind of gave up, and I don't even know how to move my world over from Wii U without homebrewing, so I'm not gonna be doing that, I guess. But it would be great if I could move it over to Java. So yeah, that's why you're seeing these not so pretty creations, because those are years old. Anyway, bye.